In this video, we're going to start to look at the proteins that are in your cell membrane. So we're going to start with your integral proteins. And integral or intrinsic proteins are those that associate very tightly with the membrane and cannot be removed from the membrane. They're integral to being inside the membrane. And they interact with your hydrophobic interactions. They interact with the tails, and you also have some polar amino acids where the head groups are at. These proteins are amphiphiles. You have the polar amino acids on the outside interacting with water, and again your nonpolar amino acids on the inside. And you can have parts of your protein that goes all the way through the membrane. We call these transmembrane. So a protein is a transmembrane protein if it completely spans your membrane. So if you look here, on the outside of the protein, you'll see you have a lot of polar and charged amino acids. On the outside here, we have a lot of polar and charged amino acids. However, on the inside, you have nothing but hydrophobic amino acids to interact with your bilayer. Then you have a glue and a sur. These are interacting with your head groups. If you look at your hydrophobicity index, again, you can predict where through the membrane your proteins will go. If you remember, positive numbers mean hydrophobic. So here we have one part of the protein that spans the membrane. Here we have 1, 2, 3, 4, 5, 6, 7 different spans of the membrane. And you can just see where they go in the membrane because it will be all hydrophobic residues. Now, to go through the membrane, you usually have some type of secondary structure because you need to interact with the lipids while shielding your polar backbone. Remember, the backbone is made of an NH and a C double bond O. These are polar molecules, and so they're not going to want to interact with the lipid tails. They want to hydrogen bond. And so to go through the membrane, all transmembrane regions that we know of so far are either going to be an alpha helix or beta sheet, and they're going to connect through these hydrophilic loops. So let's look at alpha helix, and it makes sense that they're shaped this way because the helix, you can have hydrophobic residues interact with the lipids while the backbone is interacting with itself to form hydrogen bonds. And so you are shielding your backbone while interacting with the lipid. So it makes perfect sense why you will find alpha helixes in the membrane. While for beta sheets, what usually happens is that you form a barrel so that the amino acids on the outside of the barrel are going to be hydrophobic to interact with the lipids. And again, your backbone atoms can be hydrogen bonding with each other in this beta sheet. And you'll find what are called these beta barrels. You see beta sheets forming a barrel. You'll have this in your pores or channels that are in the outside of gram-negative bacteria. We also see these in Mitochondria and Chloroplasts. Again, this is another piece of information or proof that our mitochondria and plant chloroplasts have come from a prokaryotic organism that the early eukaryotes more or less took over and had a symbiotic nature with, because we don't find these porins in our cell membrane, but we find them in bacteria in our mitochondria. And here they form a trimer. So here are three beta barrels forming this trimer here, and this allows the entry of nutrients in water. So the inside of these channels can be hydrophilic, the outside hydrophobic, and so hydrophilic molecules can go right through the channel. So that's how you can get water and nutrients in. And that's it for this video. I will see you in the next one.